Hey everyone, welcome back. Let us continue with second type of asymptotic notation, which is nothing but big omega. Big O gives us the tightest upper bound, whereas big omega refers to highest lower bound. Let us take the definition of big omega. The function f of n is equal to big omega of g of n if and only if positive constants c and n naught such that f of n is greater than or equal to c into g of n. For all n greater than or equal to n naught. Let us try to understand this definition with an example. We'll take the same example here. F of n equals 2n plus 3, and the definition says f of n should be greater than or equal to c into g of n. We know f of n, which is 2n plus 3, greater than or equal to something. I need to write something here. So the value of right hand side is always lesser than the value of left hand side. Let's consider c into g of n as 1n. We'll validate whether RHS is lesser than LHS. We know left hand side 2n plus 3 is greater than or equal to 1n. Let's take n as 1. We'll substitute the value of n in this equation. 2 into 1 plus 3 is always greater than 1 into 1. 2 plus 3, 5 is greater than or equal to 1. And this condition holds good for all n greater than or equal to 1. Since the condition is holding good, we can conclude that the time complexity of 2n plus 3 is big omega of n, which is nothing but g into n. Instead of 1n, we can also take log n, even that holds good. We can also take root n, even this condition holds good for big omega definition. Now let's see this time function in all types of time function. Where does that land and what are all the lower bounds that gets accepted for big omega? We have 1 less than log n, less than root n, less than n square, n cube, goes till 2 to the power n, 3 to the power n, goes till n to the power n. Now our time function is landing here. All the time functions before n, including n, are considered as lower bounds, and all the time function after n are considered as upper bounds. My bad. And this alone is considered as average bound, which is both lower bound and upper bound. For big omega definition, even the time function log n, root n will also holds good, but we always take the highest lower bound. Which is the highest lower bound here? N, right? As we have seen in our example, the highest lower bound is n for 2n plus 3 function. Let's consider same car example here. Let's take your car's minimum speed is 100 km per hour. Is it not true if we say car's minimum speed is at least 10 kilometers per hour? Yes, this is true. Can we not say car's minimum speed is at least 30 kilometers per hour? This is true. Can we not say car's minimum speed is at least 90 kilometers per hour? Yes, even this statement is also true. In this case, all these three statements are true, but 100 kilometer per hour statement is only useful, and that is the tightest lower bound for car's minimum speed, meaning highest lower bound for car's minimum speed. I hope this concept is clear. You may be having a doubt why time complexity always prefers tight bounds. Because in algorithm analysis, we want clear performance expectation and fair comparison between the algorithms. So we always choose lowest upper bound for big O, highest lower bound for big omega, which is nothing but tightest upper bound and tightest lower bound. Let us move on to our third notation, which is nothing but theta notation. Theta notation always refers to the tight bounds. That means theta notation shows the exact growth rate of an algorithm. It also shows functions as both upper bound and lower bound, which is big O and big omega respectively. And both the bounds are of same order. In simple words, theta notation tells us how a particular function grows exactly like. I hope this thing is clear. Let us see the definition of theta notation. The function f of n is said to be theta of g of n if and only if positive constants c1, c2 and n naught such that c1 into g of n is less than or equal to f of n, which is again less than or equal to c2 into g of n. This expression is nothing but a combination of both big O and big omega. Let us consider the same example here. F of n equals 2n plus 3, and as per the definition, we need to find out c1 into g of n, which is less than or equal to f of n, and c2 into g of n, which is greater than f of n. We'll consider the same example here, wherein we take c1 into g of n as 1 into n, C2 into g of n as 2n plus 3n, which is equals to 5 into n. We have already discussed 1 into n and 5 into n. Let us substitute these values in the expression and we'll validate whether this holds good or not. 1 into n less than or equal to 2n plus 3, which is less than or equal to 5 into n. Let's consider n as 1 again here. 1 into 1 is less than or equal to 2 into 1 plus 3, which is less than or equal to 5 into n. 5 into 1. 1 is less than or equal to 5 is less than or equal to 5. Yes, all these comparisons are holding good. Therefore, we can conclude that the time complexity of 2n plus 3 in theta notation is theta of n. This time function tells us that 2n plus 3 exactly grows like n. Let us consider some real world scenario and understand this theta notation. Let's take you drive a car from city A to city B, and the distance between A and B are n kilometers, and you will always maintain constant speed. The time taken is 2n plus 3. Here 2n is nothing but driving time and 3 is the traffic signal time. From this, we can conclude that no matter what, double the distance, time will always double. Half the distance, time will always half. Growth is always linear in theta notation. Simply in one line, we can say theta of n means no surprises, the algorithm always grows at that particular rate. I hope all the three notations are clear now. Just to reiterate, big O always gives us the lowest upper bound, big omega always gives us the highest lower bound, and theta always gives us the exact bound. I hope the difference between all the three notations are clear now. That's it for this video. In the next coming video, we'll be seeing the types of case analysis. Thank you all for watching. See you in the next one.